So in this video I'm going to be looking at the multiple choice questions for the end of unit test on gravity and electric fields. So the first question is looking at, you've got an object on the surface of the planet is radius r and has a mass m, and the weight is w. What would the weight of the same object be on the surface of a planet radius 2r and mass 2m? Okay, first thing, remember that the weight force, you've got your gravitational field constant, so you've got your masses and you've got your r squared. So what we've done is we have doubled the radius, which means the bottom line has been times by 4, but we've doubled the mass of the planet, so we've multiplied the top line by 2, which ends up, when you cancel those, as ending up half what the original force was. So the answer to this one is B, the weight force would be half. Okay, so let's scroll down. So now we've got two satellites, P and Q. They're the same mass and they're in circular orbits around the Earth. But the radius of the orbit Q is 3 times that of P. So, if you're closer to a planet, you need to orbit at a faster speed, because remember, satellites are governed by this equation here, so equating gravity with centripetal acceleration. So the closer you are to a planet, the faster you have to be travelling. So P is closer, so it must be travelling faster, which would mean it would have greater kinetic energy. So that would make it A for this one. So no need to look at the other options. A spherical planet of uniform density has radius r. Which line A to D gives the correct expression for the mass of the planet and the field strength of the planet? So let's first remember how you calculate density. It's mass divided by volume, and volume is going to be 4 over 3 pi r cubed. So then mass is going to be density multiplied by that. So essentially we're taking volume over to this side of the equation here. So it's going to be 4 over 3 pi r cubed multiplied by the density, which gives you the mass of the planet. So let's have a look. So that could be this one, or it could be this one here at the moment. So we also then need to think about the field strength. So remember, field strength is going to have Gm over r squared. Remember, for our mass, we've got this expression over here on the left, so we'd need to cancel 2 of the r's off the top line, leaving you just r. You'd still have your 4 pi, you'd still have your 3, bottom line, you'd still have your density, and then that would end up being multiplied by g. So let's have a look which of those two matches up with that, and it's this one here, so the answer to question 3 would be B. Okay, so let's move on. Okay, so we've got 2 point charges, and they're x and y, and they exert a force on each other when they're a distance d apart. When the distance between is 20 millimeters, the force they exert is 0.5 f. What is the distance? Okay, so let's think about how the force is calculated with charges. So we've got this. Now we said when they're a distance of 20 millimeters, they're at half of the force. So if the force is half, that must mean the distance has been multiplied by root 2. So then the original distance would be 20 divided by root 2, which would give you 14 millimeters. So just to explain my thinking there. So previously, when your separation was D, the force was F. Now, when the separation is 20 millimeters, the force is half of F. So if the force has halved, because this r squared on the bottom line, that must mean the distance has been divided by root 2, because then root 2 squared would give you 2, and then you have 2 on the bottom line. So your distance would have to be divided by root 2 originally. So 20 divided by root 2 gives you 14. Okay, so we've got two charges P and Q, a distance of 4 meters, and the current potential at M is 25. But what would it be if we moved it 1 meter closer to P? Well, so first of all, if we move it 1 meter closer to P, this distance here is now going to be 1 meter. This distance here, 3 meters. So originally, the potential at P would have been half of it, because they'd add together to give you V. But remember, potential is Q over 4 pi epsilon naught R. So we've got an inverse proportional relationship with R. So the new is going to be the old potential times by the old R divided by the new one, which is going to give you V. VQ, new, it's going to be the old potential times by 3. Oops, what am I doing? Times by 2, which was the old, and now divided by 3. So you end up with V over 3. So that means the total potential now is actually 4V over 3, and that is going to be equal to 33.3 which is answer C. So the key principles here were recognizing that each of them was originally half of V, and then we've got this relationship here, so essentially take the old, multiply by the old distance, divide by the new distance, same thing here, add them together, and then you get this potential here. Okay. So let's go on to the next question. So on the diagram, we've got the field lines and potential lines around a positive point charge. And we want a statement which is concerning the work done when the small charge is moved in the field. And we're looking for the incorrect one. Okay, so when it is moved from either P to Q or S to R, the work done is the same in each case. Well, that's absolutely correct, because Q and R are at the same potential, P and S are at the same potential, so it would take the same amount of work. So this statement is correct. And now if we look at the next statement here, when it's moved from Q to R, no work is done. Well, Q and R are at the same potential, so that's absolutely correct. You can't do any work if they're at the same potential. When it is moved around the path P, Q, R, S, the overall work done is 0. Well, that's absolutely correct, because you would do work to move between, say, P and Q, but you'd get the same amount of work back when you move back down again, so that's absolutely correct, which must mean this one is correct. But let's just have a quick look. When it's moved around PQRS, the overall work done is equal to twice the work done moving P to Q. Absolutely not, because let's say the work done moving P to Q is positive, that would mean the work done from R to S is negative, so they'd end up cancelling each other out. So that's actually not correct. Let's move on to question 7. So we've got an uncharged capacitor of 20 microfarads, and it's charged by a constant current of 80 microamps. Which line gives the correct potential difference and the energy stored in a capacitor after 50 seconds? Okay, so we've got constant current charging, so we're going to apply this old equation from year 12, And you've got the current is 80 times 10 to the minus 6, so let's get rid of the extra zeros straight away. And times by time, which is 50, so again let's get rid of another 0. So you're going to end up with 40 times 10 minus 4, or 4 times 10 to the minus 3 coulombs. Now V is Q divided by C, so that would be 4 times 10 to the minus 3 divided by 2 times 10 to the minus 5. Cancel those, gives you 2. Cancel those, gives you 10 to the minus 2. So it's going to be 2 times 10 to the 2. So it's one of C or D. And remember, energy stored is half QV. So it's going to be 2 times 10 to the 2 multiplied by 4 times 10 to the minus 3. So this 10 to the 2 would get cancelled out with one of those leaving 1. So you're going to end up 8 times 10 to the minus 1 divided by 2 gives you 4 times 10 to the minus 1. Remember, this is the equation we were applying there, and it's just a case of using the numbers we already have. Okay, so last multiple choice question on this paper. The capacitor or capacitance C stores an amount of energy E when the potential difference across it is V. Which of the lines gives the correct stored energy and potential difference when the charge is increased by 50%? So for a constant capacitor, Q is told you has been multiplied by 1.5, which means that V would also be multiplied by 1.5. So for constant capacitance, charge is directly proportional to potential difference. So that means it's going to be either A or C for the potential difference. And then if you think about it, if E equals QV over 2, it's going to end up being 1.5 multiplied by 1.5, which is 2.25. So that's that one, giving you an answer of C.